Hello everyone. Welcome to the first lecture in the function theoretic operator theory section of Compass. Today's speaker is Dr. Abhay Jindal, a postdoctoral fellow at University of Ljubljana. He will be talking about realization formula for functions on the unit disk. So, Abhay, since it is quite early there, I hope you had a good sleep to deliver a good talk. And thanks for accommodating yourself with our Indian time. So, yeah, thank you. You can start.
Okay. Thank you, Abhishek. So, recording has started, right?
Yeah.
And am I audible to everyone? Okay, there is no way to
Yes.
answer that.
Yeah.
So,
Yes.
all right. So, why are we talking about why are we talking about operator theoretic function theory in the first place? And how is it relevant uh, to say this group compass or complex analysis per se? Um, Suppose we have a function from disk to disk, and what can we say about this function? So as far as I know, complex analysis doesn't reveal much about such functions. I mean, yes, there is a power series, and then or we can apply the Mobius transformation and consider this as a function from disk to right half plane, and then see the Harglow's formula. But if we just have a function from say d to d, do we have any structure? So that is the question. Any structure on f? Can we write down a formula? So for instance, if we know say, so f is already from d to d. Suppose if we know it is rational and maps boundary the circle to the circle, then we know that this has to be a finite Blasky product, right? So given extra conditions, complex analysis itself give us a nice enough category of functions. But that is a very small class of functions, finite Blasky products. What we are going to do is, so can we write down a formula? Now, what we are going to do is we are going to write down a formula for such functions. That if f is a function from d to d, it has to look like this. Now, of course, there will be some operator theory, and this representation of such functions is itself operator theoretic. We will say that if you have a function from d to d, there will exist some isometry on some Hilbert space, so that the function can be written something like this. Now, and the proof of the theorem also is somewhat operator theoretic, and the tools that we are going to use for this to proving this formula, so there are basically two tools, and well, multipliers on Hardy space of the disk, and second is little bit of theory of reproducing kernel Hilbert spaces, general reproducing kernel Hilbert spaces. So anything related to multipliers on Hardy spaces of the disk, that we will prove. So we don't have to worry about that. Of course, little bit of familiarity with the Hardy space will help, and little bit familiarity with multipliers will also help. But there is a result about which from the theory of reputation kernel Hilbert spaces, which we are going to take as a black box, because we can't prove that result in this talk. I mean, even if we had time, that is just a little bit too technical for this group. Okay, so let me start by writing down the result itself, so that from the beginning itself we have an idea what we are going to do. I'm not going to start with the proof right after, then we'll develop some tools and then we'll go to the proof. So first let me write down the result. Phi is a Schur function. Schur function. So Schur function is any function from D to D is a Schur function. If and only if there is a Hilbert space H and an isometry V from C direct sum H to C direct sum H. We'll see in the proof that this isometry can also be taken to be a unitary. It doesn't matter. Such that writing B as V A B C D with respect to the decomposition C direct sum H, one has so given an isometry, we can write down this formula, and we are saying that if phi is any Schur function, then there exists an isometry such that phi phi has this representation. Now, if you see this closely, this looks like, suppose all of these are scalars, A, B, C, D, all of these are scalars, then this is, and say suitable scalars, then, or such that A, B, C, D is, is a unitary scalar such that A, B, C, D is a unitary, then phi is a single Blaske factor. So this representation is actually a generalization of the representation of, say, Blaske factor. How a Blaske factor looks like, we have given that representation that form to any function from disk to disk. I mean, this is a classical result. I think maybe more than 60-70 years old. Okay, so why does it make sense? Why does the inverse make sense? Why is it holomorphic? Quick note, since V is an isometry, D will be a contraction, meaning norm of D will be less than equal to 1. So the spectrum of the disk will be, spectrum of D will be inside the closed unit disk, and hence 1yz, if z is coming from the disk, 1yz cannot be in the spectrum of the disk. So I minus zd is perfectly fine, invertible, and I minus zd inverse will have a power series expansion, that summation z power n d power n, because norm of zd is strictly 1. So phi is in fact a well-defined holomorphic function on the disk. We are not right now saying that phi is actually a map from phi maps the D in the unit disk inside the unit disk. That we are not claiming right now. We are just observing that phi in fact is a holomorphic function defined on the unit disk D. Sorry. Okay. Now keeping the result in mind, we need to talk about some basic tools which we can afford to talk. And let's start with hard space. And although the definition of the hard space is not important to developing the tool, but just for the sake of completeness, hard space of the disk is denoted by S2D. It consists of all function from disk to C, which has power series representation an z power n, such that mod an square is finite. So this is essentially L2. Oh, yeah, same as L2. The hard space of the disk also has many definitions, and all the definition will eventually be come down to this. There is no reason we are choosing this definition. We are in fact not going to use this definition as well. Okay. H2D is a reproducing kernel Hilbert space. Okay, what does that mean? This means, well, this means that H2D has certain properties, right? We are saying that H2D is a reproducing kernel Hilbert space. But what we are interested in, or what exactly it means, is that the evaluation linear functionals are bounded. What is that? So for any z in the disk, consider the map f going to f of z, where f is coming from the hard space. Now, I mean, a priori there is no guarantee that any Hilbert function space will satisfy the property that these linear functionals are bounded. But those Hilbert function spaces for which these evaluation linear functionals are bounded, those are called reproducing kernel Hilbert spaces. And since the hard space indeed has this property that evaluation linear functionals are bounded, that means S2D is a reproducing kernel Hilbert space. And so now we invoke Rees representation theorem. That means, so this is a linear function f going to fz. So that will mean that there exists some function kz for all z in D. There exists kz in hard space such that f of z is f in a product with kz. Rees representation theorem. Okay, we are going to use this. The kernel, the Zigo kernel is, so the formula for this functions kz is given by 1 upon 1 minus zw bar. Now we can actually derive it from this definition. What is the definition of kz? Kz is the linear functional. Kz is actually the function which is uniquely obtained from the Rees representation theorem as a representation of the linear functional which is evaluation at z. So all of this is canonical, unique. So we can actually obtain this formula K from that. Now, of course, we are not going into this, and I'm sure most of you are familiar with this kernel.
So this is
And
a Bergman kernel, right?
no, this is Geo kernel.
Oh,
Bergman
right,
kernel
right.
is square
Because
of this.
it should have power too.
Yes, and in fact, any and those are called weighted Bergman kernels. And yeah, but the classical Bergman kernel is its power 2. This is called Zigo kernel. So that means that the kz at w is kzw. I'm talking about this kz. This is a function. This is an actual function on the disk. How is it defined? It is defined this way. Well, what is wrong? Okay, this is frustrating. So this is actually kw evaluated at z. Note that 1 upon 1 minus zw bar is analytic in z. So this is just an appropriate representation. Okay, now let's come down to multipliers. So multipliers is a collection of functions. So we can talk about multipliers for any Hilbert function space or any function space for that matter. But let us stick to talk about multipliers of Hardy space. A function phi say from D to C is called a multiplier Hardy space if phi times f belong to Hardy space for all f in the Hardy space. What is phi times f? This is just the pointwise multiplication. Phi times phi f at z is nothing but phi z f z. Now, if we take any function and we multiply it with a Hardy function, it may not necessarily lie inside Hardy space again. Okay, what would be an example of such a function? Well, that I mean, for instance, to begin with, we can take a function which itself is not in the Hardy space, right? And we can take then f to be just 1. So I mean, there are many such functions, and such a phi induces a multiplication operator, and we shall denote it by m phi from s2 to s2. How is it given? F going to phi f. Simple. Now, by closed graph theorem, one can check that m phi is bounded if phi is a multiplier. Okay. Now we ask the question, what what is the collection of, well, let me maybe say one remark. So similarly, one can define multipliers for any reproducing kernel Hilbert spaces. Collection of all the multipliers is an algebra, and it's direct from the definition. It's easy to check. What are the multipliers of the Hardy space? Well, it is h infinity d. What is h infinity d? Functions from disk to C such that the infinity norm is finite. The subnorm is finite. So one can check the collection of these functions from a algebra. Now, okay, I think we may not be able to prove that it is actually precisely h infinity d, and it is an important fact to obtain this realization formula. And actually, this is one of the major tool to realize that Schur functions are actually multipliers of Hardy space. They are special multipliers, in fact. Now, what we are actually going to see is that multipliers are contained in h infinity d, and the converse of this, that is h infinity d is contained in the multipliers, that comes from an integral representation of functions in the Hardy space. Uh, well, maybe we can take this also as a black box, but let us observe one more thing about multipliers. So suppose phi is in h infinity d, then we know m phi is a bounded operator, so m phi star makes sense. M phi star kw is
Hello, Abhay. I think there is some network issue.
And the screen is frozen.
Whether Abhay is there? Oh, no, I guess.
Nope.
Yeah, there's some internet issue. He will be back soon. Just wait, guys.
Hello. I'm sorry.
Yeah, all good.
Yes. Actually, my mobile went off, so I'm using the hotspot of mobile.
Oh, okay,
Uh,
understood.
so you see the screen now?
Yes, yes.
Okay. So we are going to show that if phi is a function in H infinity D, that means if phi is a multiplier of the hard space, then m phi star kw is phi w bar kw. What does it mean? It means that kw is an eigenvector of m phi star with eigenvalue phi w bar. That also means that uh, okay, that also means that the norm of m phi has to be bigger than the subnorm of phi. Okay, so let us first see this. F comma m phi star kw, this is m phi f kw, this is okay, phi f kw, this is phi w fw, this is phi w f of f kw, which is f comma phi w bar kw. So we have the result m phi star kw equal to phi w bar kw. Now this implies so this proves one side containment that if phi is a multiplier of the hard space, it has to be an H infinity function. Okay. That is all the basic theory we will need about the multipliers. Now, let me mention a result about reproducing kernel Hilbert spaces, which we are going to use. Suppose k is a positive semi-definite function on a set X. Assume that the set X is
is it imply that the norm of operator of M5 is exactly equal to this norm phi because we have the less than or equal to inequality?
Yes, in case of Hardy space, in fact, it is. In case of Hardy
Uh,
space, norm of M5 is in fact the subnorm.
right. Yeah. So I'm saying here you prove this reverse inequality and the forward less than or equality is always true. So
No,
you
no,
will
no,
get
no, no, no,
equality. Oh,
no, 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 no.
because M5 of F is 5 times F, right?
Okay, just a minute. Let me write down what you are saying.
Mm-hmm.
Uh, so you are saying that M phi of F is 5 times F. So,
5, right. So now if you
hmm,
take the norm on both sides, so it will be uh, less than or equal to 5 times norm of F, norm 5 times norm F.
how?
Okay, is it which norm? Hardy space.
So yeah, this is
Okay.
Hardy space. Here in,
Uh-huh.
let's say this is Hardy space norm.
Yeah, but you can pull it out,
So
right?
Uh-huh.
It's just L2 now.
Okay, we can't pull it out, or we can use something like this Cauchy Schwarz
no, no.
inequality.
The thing is,
No?
we to
Okay.
prove that what you are saying is in fact true in case of Hardy space, that this is. But to prove this, we need
Uh-huh.
integral representation of functions in the Hardy space.
Right. Oh, that we
So
don't have here.
this inequality, in fact, is very particular to Hardy space. In fact, it is,
Uh-huh.
you can say, characterization of Hardy, one of the characterization of Hardy space.
I see. Okay. So here
Well,
we don't have this
not
inequality
like, I
for
mean, for
general.
instance, in case of Hardy space is kind of uh, the smallest class of functions for which this can hold. It can be made precise,
Uh-huh.
but let's not go there.
Okay.
For instance, for Bergman space also we'll have this. For Bergman space also, the multiplier algebra is for whole of H infinity.
Right.
That norm of M phi is subnorm of phi there
Mhm.
also. And in fact, any kernel which has Go kernel as a factor. So suppose I have a reproducing kernel K, which is S times G, and this is 1 upon 1 minus Z W bar, and G is anything positive. Then this K will have multiplier algebra H infinity D, and norm of M phi will be, as soon as we have this, the multiplier algebra is H infinity, we know that the norm of M phi has to be some scalar multiple of subnorm of phi. And but if in this setting we'll
But
get this.
here you are saying for in general case it may not be true. This inequality norm phi f is less than or equal to norm phi times norm f.
Yes, yes. In fact, it is not. For instance, you can
Uh-huh.
say you have Dirichlet space on the disk. There it is not true.
Okay.
This one way which we have proved is true in general. That is, for any reproducing kernel Hilbert space consisting of, say, analytic functions, we will have that the multiplier algebra is contained inside H infinity disk. So this is what we prove, right? M5 will always, norm of M5 will always be bigger than the subnorm. Okay, now we need to speed up the things a little bit. Suppose K is a PhD positive semi-definite function on a set X. I'll define what we mean by positive semi-definite function. On a set X cross X, then there is a Hilbert space H. and a function g from x to h. No, we are not commenting anything more about this function. Any more holomorphic, non-holomorphic. We don't know what how x is. Even if x is disk, we are not commenting. We don't need it to be of any particular form. Such that kx by is zy gx in a product H. Now this is the result which we are going to take as a black box, but let me define PSD functions because we will encounter one to use this theorem. K from x cross x to C is PSD if for any finite set of points x1 x2 xn from n and any set of complex numbers C1 C2 Cn, we have summation Ci bar Cj kxi xj to be positive. This means that this in a this summation being positive is same as saying that this matrix kxi xj, this n cross n matrix is positive semi-definite. So, and that is why this name positive semi-definite functions. Okay. Now let us come to the proof the main result. Okay, first we will prove that suppose phi has this given form, then it is a Schur function. What does that mean? Suppose phi is of this form, a plus zb I minus z inverse c, where a b c d from c direct sum s to c direct sum h is an isometry. Then phi is a Schur function. Okay, we have already talked about that phi is a well-defined holomorphic function on disk. Now let us compute 1 minus phi z bar phi z. Well, before that, it will be good to note down some conclusions from the fact that V is an isometry. Now we will use this. So This is just a straightforward calculation. I'll do a step or two. 1 minus a star a minus z a star v I minus z d inverse c minus z bar c star I minus z bar d star inverse b star a minus mod z square c star I minus z bar d star inverse b star v I minus z d inverse c. Okay, this we have just expanded the formula for phi z and phi z bar. Now we use the isometry thing. So I minus a star a is c star c minus a star v is c star d. So we write minus b star a is d star c. So plus minus mod z square c star I minus z bar d star inverse b star b is I minus d star d. Now after some calculation it comes down finally to, and after this we don't have to use the fact, we don't have to use anything from the fact that v is an isometry. Now this is just calculations and it comes down to I minus z bar d star inverse 1 minus mod z square I minus z d inverse c. Clearly, so 1 minus, since z is from the disk, 1 minus mod z square is positive, and what we have here is an operator of the form t star. So this is positive, and that is what, so we have proved that 1 minus phi z bar phi z is positive for any z. So this proves that phi is a Schur function. And of course, this is not the main or interesting part of this theorem. The main part is to produce a Hilbert space and an isometry and to write down this formula. So now converse. Suppose we have a Schur function now. What do we know? Since phi is a Schur function, its subnorm is less than equal to 1. This will imply that norm of m phi, which is same as norm of phi, is less than equal to 1. This will imply that I minus m phi star m phi is a positive operator. Now we claim that I minus, well, this is positive, but what we need is I minus m5 star, which is also positive because m5 is a contraction. I minus m5 star so let's, for the sake of it, let's call this we are defining a new function k tilde z comma w I minus m5 star kw in a product with kz. Now we claim that k tilde is a positive semi-definite function. How do we prove that? To prove that, we need to check that summation ci bar cj k tilde zi zj. This should be positive. Let us check summation ci bar cj. What is k tilde zij? This is inner product I minus m5 star kzj kzi. Okay. Now what is this? Let us. This is summation I minus m5 star summation cj kzj summation ci kzi. Note that these are the same summation czj kzj. After summing it all, these are the same function. And I minus m5 star is a positive operator, so this is positive. So we have proved that k tilde is a positive semi-definite function. Okay. So by this result in the black box, where is it? Where is the black box? This. We will get that there exists a Hilbert space and a function h and g from x to h such that k tilde, well, x here is actually disk, so k tilde of z comma w is gz zw. Now let us expand k tilde zw a little bit. What is k tilde zw? K tilde zw is I minus m5 star kw kz. Now this is kw kz minus m5 star kw kz. This is kz comma w minus, well, m phi star kw is phi w bar kw, m phi star kz is phi z bar kz. So we get 1 minus phi z phi w bar kzw. So this is the form for k tilde zw. So what we have is 1 minus phi z phi w bar kzw equal to gz. I'll take maybe, I'll finish by 8:40 my time, so I'll take maybe 10 more minutes. gz gwh. Now what is this kernel? We know the formula for the GGO kernel. So this is 1 minus phi z phi w bar 1 upon 1 minus zw bar equal to gz gw. This implies 1 minus phi z phi w bar equal to 1 minus zw bar gz gw. This implies 1 plus z gz w gw is equal to phi z phi w bar plus gz gwh. Now this representation gives us an opportunity, this identity gives us an opportunity to define an isometry, because what we have that two positive quantities are same. So we define an operator from C direct sum H to C direct sum H by sending one z gz. Note that z is an scalar, gz is an element in H. So one z gz is an element in C direct sum H. We send this to phi z gz. Now phi z is an scalar, gz is an element in H, so this is also an element in C direct sum H. So this is what we does. Now of course 1 z gz, so clearly this defines an isometry. It's an isometry because of this identity we obtained earlier. Defines an isometry on span closure of 1 z gz. Z belong to disk. Now this may not span whole of C direct sum H, so there will be something left in C direct sum H. If dimension of that space is less than or equal to the dimension of the space left in the range side, then we can just send that to, we can pick up an orthonormal basis of the orthocomplement and send it to some orthocomplement, some orthonormal basis of the orthocomplement of the range. But if it is not, suppose there is a possibility that what is left on the left hand side is more than what is left on the right hand side. Maybe right hand side has covered whole of C direct sum H and left hand side has not covered whole of C direct sum H. Then it's a problem. Then we cannot define an isometry, right? So what we do, we add another infinite dimensional space in H. So say we add L2. Okay, so instead of the H, we will have H direct sum L2, and that will be a new H. And then we will have infinite dimensional spaces left on both sides, and then we can happily define an isometry between these two, or rather a unitary between those two spaces. We don't care how B is going to behave on the ortho complement. All we care is about is this subspace of C direct sum H. Okay, now we write that isometry has been defined. So we write V as A, B, C, D. Is it clear to, it is important that it is clear that how we are defining V. I have not logged in my laptop. So if anyone can see that there, if anyone has any question, please speak up. If it is not clear how V is defined. Okay, let us move forward. We write V as A, B, C, D. I mean, this is just the decomposition. And what we have then, A, B, C, D, 1, Z, G, Z. How, where it is going? It is going phi Z, G, Z. This implies A plus Z, V, G, Z is phi Z, and C plus Z, D, G, Z is G, Z. So let us call this 1, 2. From 2 we solve for Gz. So we have C plus Zd Gz equal to Gz. This implies I minus Zd Gz equal to C. Now we know that I minus Zd is invertible. This implies Gz equal to I minus Zd inverse C. Now we put it in 1 to obtain a formula for phi Z. Phi Z is A plus ZV I minus ZD inverse C. Okay, so we have proved the formula. I want to make a comment or two before I end this. Let us go to the beginning. Why? Okay, so what? We have a formula. Now, first comment is that what happens if H is finite dimensional? See, if H is finite dimensional and V is an isometry, then it becomes an unitary. And it, in fact, note that if H is finite dimensional, D is a matrix, finite dimensional, so it will have finitely many eigenvalues. So I minus ZD inverse will have only finitely many problematic points. I mean, that means it can have only finitely many eigenvalues on the circle. So that will mean that, or it can also be written as adjoint of A, I minus ZD. So A inverse is adjoint of A by determinant of A. So, and so determinant of I minus ZD inverse will be a polynomial in Z which can have only finitely many problematic points. So that will be in that phi is a rational function. Okay, so in nutshell, what I'm trying to say is, if H is finite dimensional, then phi is a rational function. But since B becomes unitary, phi actually becomes rational inner. So that means we cannot expect a converse, right? That if phi is a rational, then we have finite dimensional realization. But if we relax that, if we don't want V to be isometry or unitary, we just want it to be a contraction, then we do get a finite dimensional realization for rational function. That is, if phi is a rational function, then there will be a contraction and a finite dimensional Hilbert space H, such that we will have all of this. And if phi is rational inner, then we will have unitary, finite dimensional space, and this representation. Now, I don't know where it will be used. It may be useful in complex NF, but it has been useful at least in solving Nevelina-Peck interpolation problem. And if anyone wants to see how it has been used in solving Nevelina-Peck interpolation problem, then I can suggest a reference. And the reference is, just a minute, let me be sure about the title. Yeah, there is a book. Yeah, and one we have also recently we have proved a result using realization formula, and what we have proved is a theorem of Carré-theory, a classical result in complex analysis, and using this realization formula technique, we have proved a purely complex analytic result. So for the use of this in the Peck interpolation, see the book Peck interpolation and Hilbert function spaces. And to see the result proof of Carré-theory using dilation, see our paper. I have forgotten the title of my paper, just a minute. Approach to Carré-theory, just a minute. A dilation theoretic approach to approximation by inner function. अरे dilation. Okay, I'll end the talk here, and if anyone has any relevant question, then they can ask.
Okay, thank you, Abhay. Do we have any question? Just one question I can see in the comment box, Abhay. So it is,
Okay.
Does multiplier algebra for general HP spaces is also H infinity, where P is not equal to 2?
What is when P not equal to 0?
P is not equal to 2. I mean, he has just rectified it.
Okay, sir. Yes. Okay. Yes, I think for those also, I mean, I've never studied the multipliers for Banach spaces, because I mean those SPs are Banach spaces, not Hilbert spaces. But yes, multiplier algebra for them also will be H infinity, because they also, all of them have integral representation. Instead of the integral representation, instead of power 2, they have power P. just like LP norm, and so the phi will simply will come outside. I mean, in as far as I can see the picture. So I think yes, the answer to this question is yes. I mean, for those P when HP is a Banach space, of course.
Okay. I don't know whether that person can hear the thing or not.
What?
I don't know whether that person can hear your answer. Okay, yeah. He said, okay, thanks. Yeah. I think he is unable to on his mic actually. Okay, anyway, he said thanks.
Yeah, I have a question. So,
Okay.
the integral formula you are talking about, is this just the Cauchy integral formula?
No.
Which one? Then?
You want have to. I don't want to make a mistake, so let me just be sure about the constants and all. Give me a minute. I'll show you
Yeah.
the references. Yeah, so there is a result in the book of Rosenthal which says that basically, yeah, integral representation of the norm, not of the function. So and then so what we are saying is f is in S2 if and only if this quantity is finite, and then it also turned out to be the norm square.
Yeah.
So
Yes.
suppose instead of f, if we have phi f, then we have phi f here, then we can write less than equal to, and the supremum of phi can come outside of the integral, right?
Yeah, I understand.
So from here it is clear that if phi is an H infinity function, then it is a multiplier.
Yes.
And I think similar kind of instead of power 2 here we will have power p when we talk about
P.
HP.
Yeah. Do we have any other question? Anyone? Okay, so if not, let us thank our speaker. Thank you, Abhay.
Okay, thank you.
We will close this session and we'll meet in the next session. Thank you, everyone.
Okay.